Welcome to the third talk in my series of talks on higher connectivity and excluded minors. In this one, we'll actually pull together some of the stuff that we did in the previous two talks and then take it forward. So I'll begin with introduction and definitions. And this is designed as a standalone talk. If you missed the previous two talks or you don't want to go through the details in the previous two talks, I think this would be fine as is. Then we'll talk about connectivity and then three connected graphs in particular, and then focus on one excluded minor theorem. So graphs in this area have parallel edges and loops, and if we want them to not have parallel edges and loops, they are called simple graphs. I should have done this before, but I think there is a seamless or single page or something. Yeah, that's better. So a graph H is a minor of a graph G if H can be obtained from G by deleting edges and any isolated vertices or contracting edges. So deleting edges is easy. In this example, if the edge E is as shown over here, deleting edges simply amounts to erasing the edge E. And that's how you get the graph on the right. Now, if you delete enough edges and you form isolated vertices, then just delete those isolated vertices. The other operation involved in minors is contraction. And in contraction, you take this edge E and sort of squish it down and identify these two vertices, V1, V2, as one vertex V. So that's G contract E, and the operation is written like that. G delete E is written in this manner. So so a minor is obtained from G by deleting edges and any isolated vertices or contracting edges. And in some cases, we have to talk about proper minor, and that just means that it's not empty or G itself. Now let mu be a class of graphs closed under minors. What does that mean? That means that if G is in mu, then G delete E and G contract E also has to be in mu for every edge of the graph. So for example, the class of forest is closed under minors, since a minor for forest is also forest. The class of trees is not closed for a technicality, because if you remove an edge, then you disconnect the graph and you get a forest, right? So it's just a technicality there. The class of planar graphs is closed under minors. And this interesting family, series parallel network, which is a multigraph obtained from a loop or a single edge by subdividing edges or adding edges in parallel. So you can subdivide edges, or you can add edges in parallel, and so grow the graph in this manner. So the class of series parallel networks is also closed under minors. So three classes here: forest, planar graphs, and series parallel networks. So a minimal excluded minor for mu is a graph that is not in mu, but all of its proper minors are in mu. So the historical first result on excluded minors is this one by Kuratowski-Wagner. A graph is planar. A graph is planar if and only if it has no minor isomorphic to K5 or K33. That's K5. And that's K33. So the history over there is interesting. Kuratowski proved the result in terms of subdivisions. A graph is planar if and only if it has no subdivision isomorphic to K5 or K33. And then Wagner came in and said, well, it's minor, and it's a small argument to go from there, from Kuratowski's theorem to the minor version, and this theorem is now called the Kuratowski-Wagner theorem. And historically, it's the first excluded minor theorem. But the one that we would do first is actually this one because of how simple it is. A graph is a forest if and only if it has no minor isomorphic to K3. So K3 is just that. Okay, so I see there's a couple more people. So welcome. We just started. We're just talking about excluded minor results. So let's quickly go through the proof here because of how short it is. Well, one direction is straightforward, right? I mean, if K3 is not a forest, right? So the smallest graph that is not a forest is K3. Since a class of a forest is closed under minors, if G is a forest, then G has no K3 minor, right? So that direction is immediate. So this direction is immediate. If G is a forest, it has no K3 minor. K3 is not a forest. Conversely, suppose G has no K3 minor. And suppose, if possible, G is not a forest, then it has a cycle, right? It has a cycle, and then you can just contract down that cycle to get K3, which is not permitted. So that takes care of that result. Both directions are quite simple. It's more of an observation than a theorem. Any questions so far? Is this good? So this is like practically the first excluded minor result that is done. Okay. Just please stop me anytime, okay? So this is now a repetition. There's parts of this that repeat the material from the previous two talks and pull it all together. So a clique is an induced subgraph that is complete. And suppose G1 and G2 each has a clique. The clique sum across KT is formed by placing two copies of KT, one on top of each other, and identifying the vertices and edges. So for example, this would be if you have G1 and G2, you can attach it at any vertex like this, and this would be the clique sum across K1. So if you want to attach across K2, K2 is an edge. So here's an example. So you attach it across the edge and you get this graph here. If you want to attach it across a triangle, so this is where the bit about placing two copies of KT become a little bit more needed. In the previous ones, you're just kind of sticking it across a vertex and an edge. So you're kind of placing the two copies of K3 one on top of each other. You're identifying it, and then this is the resulting graph. So this would be the clique sum, right? So the edge stays. In the T sum, the edge is removed. Of course, for one sum, clique sum and T sum are pretty much the same, and we don't really put the one over there. But for two sum, the edge is removed, so that's why it's dotted. Three sum, the edge is removed. All right, so that's clique sum and T sum. And then we have another proposition that's really just an observation. If G is, a slight misordering. I talk about connectivity much later, but this is just connected. But I guess I have kappa G over here, so it should have come later. But anyway, this is the third talk, and we've done connectivity in detail in the first two talks. So kappa G is 1 if and only if you can write G equals H1 plus H2, where H is HI connected minors of G and probably should be moved just for the sake of the ordering. All right, so here's higher connectivity, and that theorem should be on this slide. Let G be a connected graph A set of vertices whose removal disconnects G or results in the trivial graph is called a vertex cut. This is how we started talk one. So the connectivity of G denoted by kappa G is the size of the smallest vertex cut. And if G is K connect, we say G is K connected if kappa G is greater than or equal to K. So this definition is a non-trivial one. And the speed at which I have said it is not exactly conducive to understanding it, but this is explained in detail in talk one. And this is just in talk three, we're just sort of summarizing everything and pulling it all together. So yeah, some people say that, the graph has to have K plus 1 vertices if you're talking about removing K vertices. Any questions so far? Or is the speed okay for this material? Okay. Maybe give me a thumbs up or something just so that I know, because I know that when I talk fast, I kind of, yeah, thank you. I pick up speed yeah. So, so then we have edge connectivity, which is, it's interesting. And there are some details in, the next sequence of talks would be on matroids. And then we would have to talk about a very careful translation from graph connectivity to matroid connectivity, but it doesn't matter for three connected graphs, so we can, avoid some details that would be needed in a matroid talk on connectivity. But in any case, one must know edge connectivity. A set of vertices whose removal disconnects G is called an edge cut. The edge connectivity of G,
edges whose removal, right?
whose a set of edges, yeah. Yes. Yeah, this is, thank you. This should be lambda, right? And this should be edges. Thank you very much, Arshia. Yeah. So a set of edges whose removal disconnects G is called an edge cut. The edge connectivity of G is lambda G. We say G is K edge connected if lambda G is at least K. And in short, G is cut and paste error here. G is K edge connected if at least K edges must be removed to disconnect the graph. And the first proposition is essentially showing that kappa is less than or equal to lambda. This part was obvious. This part actually required quite a bit of a proof, right? So that took a while. And actually, this is one thing that there's this proof in my book needs a little bit additional stuff, which is why I focus so much on it in talk one. The proof in my book is too abbreviated. So corollary two, from this we get this very nice result that the number of edges is at least n lambda G over 2, and then immediately after that we can say it's at least n kappa G over 2. And for three connected graphs, we have M is at least 3n over 2. So this is a very useful result to know, because for three connected graphs, if you think of it as starting with 6 vertices and six vertices and 9 edges, right? So this would be 10, 11, 12, all the way up to 15, 7 vertices, 8 vertices, 9 vertices. So here we have the prism and K33. And we can sort of stair step our way up like this. This is actually a very useful way of thinking about these things, but just getting to the point where we start with prism and K33 was pretty much the subject of talks 1 and 2. So this figure sort of summarizes a lot. All right, so then we did a graph is two edge connected if and only if every edge lies on a cycle. And I just realized I thought I had more than 29 slides. So let me just see what happened. I might just switch to the, wait, 1 second. I'm pretty sure I had more than 29 slides on this talk, or maybe it was just 29. Let's see. Oh, it's 29. Yeah. Okay. So continuing. A graph is two edge connected if and only if every edge lies on a cycle. That was a short proof. Then a graph is two connected if and only if every edge lies on a common cycle. And that was a long proof. As a corollary, we got G is two connected if and only if every pair of edges lie on a common cycle. So all of these results feed into additional results that we will need. It's sort of a progression. There's a couple of corollaries here and there that are not needed, but otherwise it's a long progression into the big theorems that we need. So then we did on talk 1, we did path additions and cycle additions, and this result is just interesting in its own right, regardless of excluded minor theorems. So let G be a graph and H an induced subgraph of G. All right, so consider G minus H, leaving intact any isolated vertices that may be formed. And a path addition, so now look down here, a path addition to H is a path in G delete H connecting two distinct vertices. And the word year is actually a very nice visual, a word that captures what you're looking at over here. So the definition is formal and technical, but you just have to think of it this way. This is a path addition. You pick two vertices in H, right? And your path has to be outside H. So that's what all that stuff is saying. And if the two vertices are not distinct, that is, they're the same, then you have what is called a cycle addition. And this is a closed year. I think the closed year is just called year, but this is called open year. And a year decomposition of G is a partition of the edge set into a sequence of years where the first year C0 is a cycle and the rest are path or cycle additions. And an open year is formed only by path additions. So the two big theorems here, and actually the second bullet can be obtained from the first one, is a graph is two connected if and only if it has an open year decomposition. And two edge connected, you're permitted to have closed years. So now this is yet another characterization of two connected graphs. And that's what we have here, multiple characterizations of two connected graphs. All right, moving on.
Is the proposition 5 some way a reformulation of the Whitney's characterization theorem? Because you take the two internally disjoint paths, union of two internally disjoint paths, you get a common cycle, right?
Yeah, so all of this feeds into the proof of Whitney's theorem. I think that's how I did it in talk 1, right?
Yeah.
So this is like feeds into into Whitney's theorem. Yeah. And so that's why the proof over there is so didn't use Whitney's theorem. Okay. Yeah. And then we come to Whitney's theorem, and I actually didn't put Menger's theorem. Whitney's theorem, the way I presented it, I think in talk 1, I presented it as a corollary of Menger's theorem, but it's equivalent. So I just have Whitney's theorem here because the setup for Menger's theorem would take up a bit of time. So a graph is k-connected. This is a very non-trivial result if and only if there are k pairwise internally disjoint paths between every pair of distinct vertices u and v, and all of those results sort of feed into the proof of this result. So it is a big theorem, and its proof is really worth seeing. And that's what we did in talk one. We did the entire proof of this result, even if we skipped the proof of Menger's theorem, but we did a lot of the components. And then, and only then, I think we can conclude that if G is a three-connected graph, then G has a W3 minor. So the starting point, right? So the starting point for the analysis of three connected graphs is W3 or K4. And then the argument is just really straightforward from Whitney's theorem. But of course, Whitney's theorem sits on top of all those other theorems. And so if G is a three connected graph, then it has a W3 minus. This is W3 right here. And I believe this is where I stopped in the first talk. Or maybe I did these, I'm forgetting. So another result that we can get is that if G is a three connected graph except for W3, then G has an edge E such that G contract E is three connected. So we get that very easily from the previous corollary. So it's a corollary to this corollary. So if G has a W3 minor, then G is a three connected graph, then and then you have to have some edge that you can contract and get W3. And we're not requiring a three connected graph to be simple. So in the definition of three connected graph, you can have parallel edges. If we want to talk about simple, we'll specify simple graphs. And this is actually where the distinction between graph connectivity and matroid connectivity starts to kick in, because some of the big structural results that we'll talk about later are really matroid theory results. In matroid, k-connected matroids don't have cycles smaller than k. Whereas, in three connected, k-connected graphs can have cycles smaller than k. But in three connected, a cycle smaller than three is essentially a loop or a parallel edge. And because of that, our theorems have simple graph, and we don't need any further hypothesis. So anyway, a series parallel network that we talked about earlier is a multigraph obtained from a loop or a single edge by subdividing edges or adding edges in parallel. And after all this, we can characterize series parallel networks. G is a series parallel network if and only if it has no minor isomorphic to K4 or W3. And it was a natural question, right, to ask what sort of graphs have no minor isomorphic to K4, because we did, and G has no minor isomorphic to K3. If and only if G is a forest. So it's a very natural question to say, what about K4? And we have the answer here, okay? G has no minor isomorphic to K4 if and only if it is a series parallel network. This one requires all of those previous ones. So this is a non-trivial result. All right, moving on. Any questions so far? All good? Yeah, so then we had that result that, kappa G is equal to 1 if and only if G could be written as the one sum of its proper minors, right? So the analogous result for two connected is here. And this is now, I believe, the beginning of talk 2. So kappa G is equal to 2 if and only if you can write G as the two sum where each of H1 and H2 is a two-connected minor of G and some conditions on edges. And as a consequence, we can conclude that if G is a simple connected graph that is not three connected, right? So if G is not three connected, then G can be constructed by repeated one sums and two sums from trees, series parallel networks, and its three connected proper minors. So this was actually the last thing I did in this talk, and I wanted to flesh this result out a little bit more. It is, I think it is Tutt's decomposition theorem. And it has a number of different ways of expressing it. This is one of the slightly looser ways of expressing it. And I just ran out of time and didn't have time to flesh this out into a proper theorem and its proof. So I will save this for some other time. But the basic idea is that if the graph is not three connected, we can construct it from its simpler minors. Okay. So now let's talk about the structure of three connected graphs. And here I want to talk about the opposite operations of deletions and contractions. And they for lack of a better word, we call these edge additions, right? So it's opposite of deletion. And when we add an edge, we'll use this notation G plus E. It's a bit overused. It could mean other things, but in this context, it's going to mean an edge addition. And then just one thing to note that the edge is not simple. Don't add an edge. I mean, these are multigraphs, so you might think, can we add an edge in parallel? Well, you can, but we don't want to here. And that way, if G is three connected, then, well, even if you added an edge in parallel, this would be true, but we just don't want to. If G is three connected, then G plus E is also three connected. So now the vertex splitting operation is a little bit more involved, but I think the intuition is really important here because the details, with just the details, you can get really lost in the details. There are more details than this. And the intuition is in contraction, right? You take a vertex. No, I can do it just one. In contraction is this way. You take vertex edge F, it has n vertices V1 and V2, and you just contract it down. So this direction is contraction. And this direction is vertex split. So it's actually an edge operation, even though the language says vertex split. We want to think of it as an edge operation, so we kind of denote it like this, G dot F. Again, for lack of a better notation, there could have been a better notation for this, but this notation really pushes the theory forward. We need a notation for G plus E, and we need a notation for this operation, and we are going to use G little circle F. If you can think of a better notation, I'll be happy to hear it. I've got about 5 or 6 papers using this notation, but it's never too late to switch to a better notation. And there are quite a few details to conclude that they are opposite of each other, especially when the edge is in a triangle and things like that. But the intuition is this, that you take a vertex and split it up, break it up like this, and you just make sure that you give at least 2 neighbors here to V1 and V2. And that, again, is not necessary in general, but it's necessary if you want to preserve three connectivity. All right? So the main thing about vertex split is that you can get many. So I feel like this example is key This is K5. If you split this vertex V, you get so many possibilities depending on how you link up the various edges A, B, C, and D. And in this being K5, they're all isomorphic. So it kind of belies the point, I think, that you actually get non-isomorphic ones, but this is another example. And the only vertex split of K5 is this graph here. And the next example is a little bit better. You can see how you can split the red vertex or you can split the green vertex. You get 6 splits if you look at all possibilities and of red vertices, 6 splits of green vertices, check isomorphism, and then you actually get only 3 vertex splits. And this is something that can be done. These are small graphs. It's very, very doable to do these things by hand to get a sense of how this works, right? You just have 12 things to check over there, and then you conclude that there are just 3 non-isomorphic copies. But if it gets larger, like even slightly larger, then you've got a lot of things to check. So it is easy also to use software to check vertex splits and edge additions. And OID, my Matroid software, OID does these things, but it's Matroid, so the learning curve is steep. And, when we're just talking about graphs, we don't need that machinery. Fortunately, Claude Code is there to help us, and now we can just ask it to put together something that checks. However, isomorphism is non-trivial, and in all my isomorphism checkers, I use Brendan McKay's Naughty, which is one of the best isomorphism checkers. So I'm not sure Claude Code can put together an isomorphism checker. So there you have it. Yeah, so things have improved, but maybe not too much. Okay, so now let's talk about Tut's-Weil's theorem. This was toward the end of talk 2, and we had many different versions of Tut's-Weil's theorems. And all of those versions play a role in this, so they're all important, but in this summary talk, I have reduced the versions. The main thing about Tut's theorem, and this is a big theorem, and the proof is really something that we should go through in detail. So that would be, sort of another talk, practically a whole talk, maybe 2 talks to get through the proof of Tut's theorem. But the basic idea here is that wheels are special. So these are the single element deletions of a wheel. You can delete a rim element, and then you get this graph here. Or you can delete a spoke element, and then you get this graph here. Neither of them are 3 connected, right? These are not 3 connected. And now let's look at a contraction. So you can delete a rim element edge. I do say elements. Sometimes I slip into Matroid language. So edges are the elements in the Matroid. So if I'm suddenly talking about elements, it's really edges that I'm talking about. And if you delete this edge, you get this graph, which is 3 connected by a definition, but not simple.
You mean contract, right?
Sorry, contract. Yes, thank you. Yeah. And if you contract this edge, right, then you get this graph. And that is not 3 connected, right? Yeah. So wheels are very special. They're the only ones with this property. Now, we saw earlier that if you have a graph, a 3 connected graph, then because of all those results we did, we can get an edge. We can find an edge, right? A G is 3 connected. Implies there exists an edge E such that G contract E is 3 connected. But Wheel's theorem says so much more than that. right? It says so much more. It says that, sorry, I can stay right here. Wheels are the only ones with the property that G delete E is not three connected, G contract E is not simple three connected. All right, so wheels are really, really special. And it's saying a lot more than this result here, which we got from all those other results previously. Now, the way, so we have to prove Wheel's theorem, we would prove this, and then these would actually be, small corollaries of the Wheel's theorem. So wheels are the only simple three-connected graph with a property that G delete E and G contract E are not simple three-connected, right? That means every other graph will have an edge E such that G delete E or G contract E is simple and three-connected. And the simple and three-connected is important because this was obtained much earlier, right? There's always going to be an edge such that G contract E is three connected, but just to get simple and three connected, either there will be some edge such that G delete E or G contract E is simple and three connected. And for the excluded minor results, we need the constructive version, even if we sort of present in our induction argument the top-down version. We really need this constructive version, first of all, to find the result and spot the pattern, and then also the way we do the induction to some extent. So this is the constructive version. The operation opposite G delete E is G plus E, and G contract E is G dot E. So what this is saying is that if G is a simple three-connected graph, then there is some other simple three-connected graph such that G dash plus E will be G or G dash dot E equals G, okay? So you can grow them. You can go from G down to a wheel, right? Or you can grow from a wheel up to G. That's what the Wheel's theorem is saying. I don't know what the word opposite grow is, but can go from G to a wheel, preserving three connectivity at any stage, doing deletion contraction, preserving three connectivity, and can grow up to G from a wheel. How do you grow? You grow by adding edges and splitting vertices. All right, so this is where we stopped, I think, in talk 2. And I hope that seeing it all together, fills in some of the gaps, because we were really down in the weeds in talks 1 and 2. So I'll pause a moment and let you read the famous splitter theorem. In this presentation, it appears in decomposition of regular matroids as a matroid result, but then 2 years later, Nagami gave a graph version of it, and I think that it would be a really nice exercise for all of us to go through Nagami's proof, because if you want to, see the proof of this result, then you want to look at Nagami's proof, not the matroid proof. And then there was a slight modification of the hypothesis made in Collard and Oxley's paper, and that's why you have this version. And it's called Wheels and Worlds theorem, actually, because it's a matroid result, but the worlds are not matroid graphs, so we just have Wheels theorem. All right, I'll pause here while you read this. Yeah, I would personally like to do this proof, and we could treat it like a study group project or something. where we read Nagami's paper and work out all the details. Okay. So suppose G is not a wheel and its H is not W3, right? And H is a proper minor of G, right? So you have G, you have a proper minor H, and just forget about the wheels. And then there is an edge E such that G delete E or G contract E is simple three connected and has that H minor. The H minor is always there. So it sounds, so essentially what Todd did for wheels, you can actually say for any H minor. And the original hypothesis is slightly different from this. This is from the last paper where the hypothesis was simplified. So at the end of the day, all of this says is that if you want to grow your family of three connected graphs, and it's always a useful exercise to generate a whole bunch of things, you can't really do anything with W3, right? That's degree 3, it's a cubic graph. You can't extend it. It's K3, it's K4, so there's no edge to add. You can't split any vertex. Then you just look at all the other three connected graphs, and you just get right down to the four wheel. And so everything begins with the four wheel. You can extend the four wheel and up to K5, and then do vertex splits of the four wheel, right? And that's what this version down here is doing. This is just the constructive version of the top down. So here, I don't know if I have it, but here, let me talk about, let me do that. So you take W4, right? Well, if you're adding an edge, the most you can do is this, right? There's no other way you can add an edge over here. So it has 4 vertices and 8 elements, and now you have 4 vertices and 9 elements, and this is a familiar graph, is K5 delete E, and you add 2 edges, right? So this and this, then you get K5. It's so small that up to isomorphism, it has just one edge addition, and that one edge addition has just one edge addition, right? So this is how you would add edges to W4. On the other hand, if you're splitting W4, you can split that center vertex, right? And then you will get prism and K33. And that is why in that stair-stepping picture, I said we can essentially start any analysis with the prism and K33, right? And that's 6 vertices and 9 edges. And then you can grow up to K6, so up to 15 edges, and that's a really good exercise to look at all of that, and then to do at least up to 7 edges, 7 vertices, all the vertex splits. All right. Yeah, so it's based on some big results. So moving on, now, the first, let me just introduce this. An edge in a 3 connected graph is deletable if you can just remove it and preserve 3 connectivity, right? So this edge here, you can remove and preserve 3 connectivity, right? Because G delete E is a prism. But if you remove this edge, then call it F, then that graph is not 3 connected. And a three-connected graph is minimally three-connected if it has no deletable edges. So, I mean, you can say it all in one sentence. G is minimally three-connected if removing any edge destroys three connectivity. And now let's introduce H minor in the picture. So suppose G and H are simple three-connected graphs such that H is a proper minor of G. Then an edge is H deletable if it is three connected and preserves H minor, right? And this is a very broad definition. It's for any H. H doesn't have to be minimally three connected. Minimally three connected graph H could be like K6 or K10 or something. And or some graph in maybe not K6, but some other graph that is very large and not minimally three connected. Minimally three connected graphs exist only up to 3n minus 9 edges. So this was the theorem that was just published in Discrete Math. And it puts an ordering on the splitter theorem. And it is a version, you can get the strong splitter theorem from this. Strong splitter theorem is a matroid result that Manuel Limos and I published in 2014, and it's just been incredibly fruitful. But when you're just talking about graphs, we can express it in a little bit simpler language than we did in matroids. And the reason for that is this. A graph sits inside a complete graph, right? So you have like a lot of structure and an object that all our graphs sit inside. Matroid doesn't sit inside in any larger objects. Certainly, matroids coordinatizable over finite fields will sit inside the projective geometry. A matroid in general does not sit inside a largest matroid, like the case of graphs or representable matroids. So the language in which the strong splitter theorem is expressed in 2014 it's not easy to understand. Let's put it that way in its full generality. And I think this is a much easier result to understand. So the splitter theorem tells us that we can go from H to G. We can grow the graph from H to G, right? We can grow the graph from H to G. We can do add edges, split vertices, and get all the way to G. But it doesn't tell us what's the most optimal ordering for doing it. And that's what this is saying, that you can split vertices and get to G, right? Or you can add an edge and split a vertex, but a very specific way it's done. The E and F are in a triad. So if you add an edge, that's the edge here. This is what we're looking at. And then you split, let's see. You add the edge. There's an added edge somewhere. And the added edge is here. I wasn't looking at the picture right. So the added edge is in red over here, right? And then you split the vertex V, but you split it so that this is a triad. Triad is just degree 3 vertex. You split it so that one side just has 2 neighbors, and then the other neighbor is going to be V1, of course. It's a very specific manner. And you can add 2 edges. So here are E1 and E2, 2 edges added to the graph. And then if you split it, it's exactly one way of doing it. And what this does is it reduces computation considerably and reveals patterns that may have been hidden and shortens proofs that are otherwise very long. Some of my proofs too that are previous to this that are very long can be shortened. And this essentially, this was a component of multiple proofs that I have done. And then Manuel Limos and I sort of realized we're doing the same thing again and again. We should distill it out into a result. And that's how the strong splitter theorem was born. And this is just a manifestation of it for graphs. So when you're growing from H to G, right, you have to contract, you have to, what is it called? Split vertices, or you add an edge and then split it in this very specific manner. Of course, you can get multiple graphs here because, the vertex G can be, the edge G can be linked to multiple neighbors, but then here you just get a single graph. And everything else will have a H deletable edge. So it tells us the most optimal way to grow the graphs. Is there any question? So the proof of this is about a page and a half and is very doable. So one talk should be devoted to doing that actual proof. Any questions? Okay. It does sit on top of the splitter theorem, which is an entirely non-trivial result. And on top of that, so maybe that's what makes this a little bit difficult. But let's look at it in action. Now, we saw previous excluded minor theorems using the notation EXK3. That was what, Forest? Then EXK4. Series parallel networks. And EXK5 and K33, that's planar graphs. That's Kuratowski's result, which is also worth doing at some point. And EXK33 is not much, actually. It's just K5 and, not much. I'll just put not much. EXK5, Wagner did. And Wagner did this result, but this class is too big for all three connected graphs. He determined essentially what is like the internally four connected ones. So then that's when the class is too big to determine just the three connected members, then we kind of raise the connectivity to internally four connected. There are some structure theorems for internally four connected graphs. And recently, there are also some structure theorems for four connected graphs. So it's very recent work on four connected graphs that I think can be used to obtain excluded minor classes of graphs that are very large. Anyway, in 1963, Dirac gave this beautiful result. It is really a beautiful result. If you exclude K5 delete E, you get a nice class, but if you exclude the prism, it's essentially the next most complicated thing to look at, right? I mean, you're dealing with all these small ones. Someone has done prism plus an edge by now, and there's about maybe 5 or 6 other small graphs that have been determined, but not much. It's just a lot of potential in this area. It's a steep learning curve to master all these structural results, but then it's just, you can really get some nice results. So anyway, so this is Dirac's 1963 result. And when the splitter theorem came out, I think there's the proof on page 26 of Balabash's extremal graph theory book uses a splitter theorem, so you condense it a little bit more than the original proof, because he did this result before the splitter theorem came out, right? So he was just using Wheel's theorem. And with the strong splitter theorem, we can condense it even more and just really boil it down to a proof by picture. And that's how mathematical research should proceed. If every result is huge and complicated, we just can't go too far forward. And this one, I'm happy to say, is just proof by picture now. Anyway, so these are the families. The small ones you would expect. If the graph doesn't have a prism minor, then K5 delete E. Prism, by the way, is K5 delete E dual, the planar dual of K5 delete E. So this is K5 delete E, and its planar dual is the prism. This is K5, of course, the wheels. And then you just have K3, K3 n minus 3 is what we're calling this, K3 n minus 3 dash, K3 n minus 3 double dash, and K3 n minus 3 triple dash. And I think I have on the next page the bit about the monarchs. Yeah. So sure, this is the extremal graph in the extremal 3 connected, I should say, in EX prism. And this one too, right? That by default, and this one too, right? So you have these 3 extremal graphs, the K5 and wheels, and this one, K3 n minus 3 triple dash, right? So the focus in excluded minor results is to find the extremal 3 connected graphs. Let's call them monarchs. I actually have that as the title of a paper. Monarch, as in that's like the largest one, right? Extremal 3 connected will just shorten to monarch. The focus in excluded minor results is finding the monarch, but actually finding the smallest one like this, and I don't have a good name for this, and this is where I would really like names. I'm going to call it seed, but seed is not a good name. It's actually these. These are in this example, it's minimally 3. This one is minimally 3 connected, right? It's actually these that are more important. Let's forget about that. That's really small. It's this one. So once you figure out the seed over here, or as if there are multiple families, then multiple seeds, then finding the monarchs are not hard because they all have deletable edges. And that's where the theorem comes in handy. It tells us how to find the seeds. The strong splitter theorem tells us how to find the seeds. These have deletable edges. That's a deletable edge, deletable, deletable. So once you find the seeds, finding the monarchs is not hard. And the strong splitter theorem gives us the most optimal way of finding the seeds. That's the key takeaway of that result. And then it just literally breaks everything down into a proof by picture. So it's an induction argument. I'm almost done, okay? I did plan to stop at 5:15 or shortly thereafter, okay? So it's an induction argument. Induction has to start somewhere, and this is where we start. We talked about how W4 has K5 delete E as an edge and K5 as double edge, right? And W4 has 2 vertex splits, prism and K33, and we are excluding the prism and seeing what we get. So you have to take K33 and grow it and hope you can find a pattern soon, which you can over here. So when you look at the edge additions of K33, this is the only edge addition without prism minor. And then this is the only edge addition of K33 dash without a prism mine, and you get the monarchs very soon. All right. But the key thing is to get from K33 to K34, right? That's the seeds. It was in green. I mean, once you figure out the seeds, growing it is quite easy. And the strong splitter theorem will tell you how to get to the seeds in the most optimal manner with the least computation. When you split this, you split it in this manner here. The EF, forms a triad. And then when you add two edges and split it, there's only one possibility. So it just kills all the computation. And that possibility is K34. Then the rest is just details. You're just proving that you're assuming the result is true for one case, one step down, and then just proving it for n. And it's all encapsulated in this figure. Getting this graph, there's so many, among all the possibilities, you can just zero in on this by the strong splitter theorem. And this is a good place to stop. Thank you very much. So I don't know why I have my hand up. Oh no, that's just my mouse. Okay. Anybody wants to say anything? I mean, go ahead. I always had a couple more things to say. I was going to say that what else is needed to kind of really flesh this topic out by proving all the results that it sits on, right? It sits on so many results. We would need to do Tutt's decomposition theorem, right? That one about the three connected stuff. But I guess that's not needed for this. We would need to do the Wheels theorem proof. We would need to do splitter theorem proof. And we would need the strong splitter theorem proof. And then this sits on top of that. So that's the part that we didn't do. And I suppose when I speak the next time, that is what I'll focus on. But next will be Anna Khan, who's speaking after spring break. Okay? I'll stop the recording.